Gmail was famously launched on April 1st, 2004. And at the time, no one knew quite what it would become. By 2012, it had reached over 425 million active users, making it the largest email service in the world. And today, Gmail users number in billions, sending each other trillions of emails that tally up to exabytes of data. Data that we need to store safely and securely on our servers. Recently, every one of those Gmail messages migrated from a legacy storage system to a brand new home on Spanner. For those new to Google Cloud, Spanner is Google's globally distributed and synchronously replicated SQL database management and storage service that horizontally scales and is highly available. A perfect choice for a planet-scale application. So how exactly did the Gmail team do this massive data migration? I invited Sudev, who leads our Gmail backend engineering team, to share this experience. Hi, Sudev.
Hi, Priyanka. Thanks for having me here. I'm really excited to be here today.
So, Sudev, I am equally excited. Thank you for being here. And more so before the migration, I would love for our audience to know a little bit more about what happens in the life of an email. So when I type this email, and we write emails a lot every day, when I compose an email and hit that send button, what's happening behind the scenes?
That's a fantastic way to start. I can give a simplified 10,000-foot view on it. After you hit send, we convert the email and attachments you are sending into the standardized email format in our delivery stack. And then we send it out to the servers responsible for receiving emails for the recipient domain. This could be an external service like Outlook, or it could be Gmail. On the receiving side, once we accept the email, we run spam, then antivirus filters, upload the attachments to our cloud storage, and then queue up the email for inbox delivery. At that point, it is routed to the user's backend service and stored. This message delivery event then results in a notification being sent to the user's device. Continuing our user journey, when the user sees the notification and picks up their phone and hits the Gmail app, we internally route their request to the correct data center holding their emails. Here, the serving stack for the user searches and retrieves the email requested by the user from Spanner. This email is sent to the user's mobile or web client as the response, and the user actually sees and reads their email. Gmail's server stack is provisioned globally, which means that we are distributed across dozens of data centers in the world. Each user's emails are stored and replicated to multiple regions. And today, all of this is done by Spanner.
So now let's dive into the migration to Spanner. So this wasn't just one of the largest data migrations we've ever done at Google, but it was one of the largest data migrations on the planet. And at its peak, just to give everybody the amount of scale this has, tens of millions of accounts were being transitioned over to Spanner daily. Where did the journey begin?
Fantastic question. So since 2010, Gmail's data has been stored in a custom storage system we built, which replicates, validates, and backs up those exabytes of user data. By 2015, the team began to seriously consider the design of the next generation of Gmail with the goal of scaling to deliver the future features. Fortunately, when we looked around, Google had already developed a solution for us, Spanner. It was more modern, globally distributed, strongly transactional, and we saw that it could scale to our needs.
That's what you needed. Now, we know that Spanner is much more reliable, scalable, but in order for it to work for Gmail, with that scale, the team must have had to transfer all of this exabyte of data to Spanner without losing a single email. That tells me that there must have been a huge amount of prep and effort that has gone into the process of migration. Would you please share the experience? How did that go about?
Yes, this was quite a feat of engineering to move an infrastructure supporting so many users while they're using it. It's like switching an engine of an airplane while we're still flying it. The last time Gmail did a migration this big was in the 2010s. And at that time, the effort to migrate was huge, even though the corpus was much smaller. We were implementing so many of those storage constructs all by ourselves, from replication to recovery.
So this all sounds very exciting. I want to dive into all of this. Let's start with the first stage.
Perfect. So going back to the first stage, this was to figure out how we could write to both systems transactionally, a first step in the journey of writing data consistently to two systems. So we decided we would commit the transaction first to the Spanner system and then stream and apply the part of the transaction that relates to our legacy storage system asynchronously using something like Cloud Data Stream. We would ensure that the legacy system has had the latest transactions committed to Spanner applied before we would allow any reads for the latest data from it.
Great. So now that we can write to both systems at the same time, what comes next?
Fantastic. So we get to stage 2, which we're talking about as the unified storage layer or the unified interface for our dual storage system. So we built a way to dual write to similar looking tables on both systems and made it configurable where you'd actually like to write it. So we did an exercise of schema mapping from our legacy storage system to Spanner, converting all those tables and making similar represented tables on Spanner. This meant that data, for the most part, could now be dual written to both systems. We also made it so that rows could be read from either Spanner or legacy system using the exact same interface. So we were able to both read and write all the supported Gmail interfaces through these two systems. This was actually a meticulous process. Ensuring both the APIs read and write consistently took quite a bit of time and rigorous testing, both for performance and correctness.
So now that we have a way to interface with the two systems using a common API, I feel that we are ready to start that migration. That must be the third step.
Yes, exactly. So now we're getting to the third step that we called the migration state machine. So once the unified interfaces were in place, we could actually now transparently read and write to both our systems. So the state machine that we designed was actually implemented by a migration server with its own Spanner storage to manage that migration process. One of the key things we decided was to do the migration on an account level, which meant that individual accounts were migrated one by one. The system ensured that the accounts went through a series of well-defined states, starting with the legacy storage system, continuing on to backfilling and dual writing, then validation, reading from Spanner, and finally deleting the legacy data. So we can dig into more of the detail here. During the backfill, we basically kept track of row ranges that were fully copied and ranges that were fully validated in a checkpoint. And we dual wrote data using our unified storage interface based on where in the migration each of these accounts had reached. And so we encapsulated all this logic for interacting with that dual storage setup into our unified interface. So our engineers really didn't have to think about what they needed to do in each of the states. The backfill was considered complete when the entire row range that existed before we had started the dual writing phase had actually already also been fully copied.
So what did you do in cases where something unexpected happens in one of these states? Let's say validation fails.
That's a fantastic question. In a system with trillions of operations a day, 1 in a billion failure cases need to be well thought about. So throughout all these migration states, one of the key reliability decisions that we made was a failure path. You could actually U-turn and unmigrate accounts in case you encountered any unexpected states like a validation issue or maybe a fingerprinting issue. And this meant that this entire unmigration process was without human intervention. So while we were going through the migration states, we actually ensured to continue to replicate data back to our legacy system until that final step when we actually deleted the data. So in case we need to revert at any point, it was possible.
That is amazing to have. Now, how do you validate that it's all been migrated safely and the user can now be sent to this new copy of data in Spanner?
That brings us to that last final stage we were talking about as validations and health checks. So after that previous backfill state we talked about, we actually ran further data integrity validators that compared data in both systems for consistency. We even validated the search indices, making sure the search results we were getting for both systems actually looked the same. Once we were done with all of our validation logic, we would actually then allow reads to go to the Spanner copy of the data. And as I mentioned before, we continued to dual write data back to our legacy system in case we needed to revert back.
Checks and balances, so important, right? What were the health checks built in this larger migration system? Now, people were still using Gmail while you were migrating. How was that taken care of through health checks?
Yes, health checks are very important when running a migration at our scale, especially so if you're doing it in a serving environment. We had both account level and system level health checks. On an account level health checks, in addition to what we already mentioned, we had an end-to-end health check before we actually deleted the legacy system's data. In this check, we simulated loading the user on our different front-end endpoints and ensured the end-to-end flow worked as expected. On the other hand, we also had system-wide health checks. At the scale of migration we're conducting, essentially rewriting all the emails over the last 2 decades, we need to make sure our serving systems were healthy and the migration load on the system didn't interfere with any other user interactions. So one key piece here was that we ensured the migration happened in a separated and isolated environment. So we de-risked any migration load causing problems to our non-migrating users. We also integrated a dynamic throttling system into the migration process. The system actually monitored for system utilization increases, crash rates, error rates increasing, or latencies increasing, and auto-throttled our copy rate when we saw any issues in our system. This meant that in a dire situation, the system stopped itself and was able to adjust its throughput completely automatically.
Auto-healing migration system sounds absolutely incredible. Thank you for walking us through the entire process.
Yes, that was a 10,000-foot view on this migration in 4 stages. Getting this right was extremely important to us. And we wanted to make sure that we kept our service reliable and kept the trust of our billions of users.
Awesome. Now, I'm sure there were some gotcha moments or memories. What are those during this migration?
There are always memories with massive migrations like this one. So we actually had these edge cases we called Spannacles. We actually came up with Spanner plus Barnacles. Barnacles are like hanging on the side of your Spanner migration ship, essentially. So these were like these edge cases that we have had in our legacy storage system that didn't just very easily migrate to our new Spanner system and kind of got stuck in our migration process. Examples of these, we had an attachment that was named longer than all the works of Shakespeare. and these accounts essentially led to us having to deal with them one by one. So we realized this early on in the migration and actually started to solve them as we were doing that mass migration.
Those are some really interesting and fun edge cases. Are these Spannacles solved now?
So yes, as of 2023, May 30th, we are actually fully migrated to Spanner.
Yay!
Every account on Gmail is backed by Spanner. And we did it with 0 data corruptions and 0 downtime. A huge thanks to the Spanner team and the Workspace team and all the hard work they've done to pull this incredible feat off of changing Gmail's storage layer while billions of users are using it. This new infrastructure on Spanner paves the way for the next generation of exciting Gmail features and improvements.
That is amazing, and I'm looking forward to those enhancements myself. Thank you so much for joining me today.
Thank you so much for having me here, Priyanka. It's been fantastic.
Whether you're migrating a huge database or a small one, the task itself is delicate because you do not want any user or user data to be impacted in the process. What can we learn from Gmail's experience? I learned about 4 things. You need to have a process, a common way to transactionally write to both legacy and new system. Create an API that's going to be that common way to read and write from both of your systems. Create a backfill system for migration, and then run validations and health checks. I definitely learned a lot. I hope this video helped you demystify how to migrate large and small scale databases effectively. We will see you next time.